We're going to continue to look at our inverse functions, and I want to start out by looking at the equation y equals x squared. So here, if we have our function, we know the graph of this function looks like this. Y equals x squared. We know that this is going to be the graph of a parabola that opens up like this. And the question is this a function? And if you think back before, how do we determine if this is a function or not? Well, remember we had all the characteristics of a function. Every x had to be matched up with a y. We could not have repeated x values. And we had a technique for using the graph. We could use the vertical line test. Remember the vertical line test? We could draw vertical lines, and if it only crosses once, then it's a function. Well, what are we testing for again with this vertical line? Well, remember, we're testing to see if we have repeated x values. We're trying to determine if one x value is going to give us two different y values, because we know that if the graph looks like this and we try to use the vertical line test, it's going to cross twice, which tells us that one x value is giving us two different y values and therefore is not a function. Well, y equals x squared. We know we can draw vertical lines anywhere through here, so the answer to this question is, does y equal x squared a function? And the answer is certainly yes, this is a function. Now we want to define something else here called a one-to-one function. Well, a one-to-one function means that for every x there's one and only one y, and for every y there's one and only one x. So we could use the similar technique, but instead of a vertical line test, we can use a horizontal line test. Well, if we draw a line through here horizontally, it's going to cross the graph twice, which means that for this particular y value, we have two x values. So here, let's say that this x value down here, when x is, let's say, a -2 or x is a +2, we're getting out the same y value here of 4. So therefore, this is not a one-to-one function. So a one-to-one function means that you cannot have repeated y values. Remember we talked about a function, we said a function cannot have repeated x, it could have repeated y. But if it's a one-to-one function, that means no repeated x values, no repeated y values. So this here is not a one-to-one function. Now, to lead into this one-to-one function, this is called the horizontal line test. Then what we need to realize is for a function to have an inverse, it must be one-to-one. So if you think about this carefully, this would make sense. In other words, if you want to have an inverse function, then your function must be a one-to-one function, which means that for every x, there's one y, and for every y, there is one x. So for example, if I look at this really quick, just looking at a table of ordered pairs, if this is your x and this is our y, and let's say that we have very simply 0, 1, 2, and we have, let's say 3, 4, and 4. Now, is this a function? Well, every x is mapped with a y, and we have what? 0, 3, 1, 4, 2, 4. Well, we have repeated y values, but for a function, that is okay. Now, is this a one-to-one function? Well, because we have repeated y values, the answer is no. So this is not one-to-one. Now, if this is not a one-to-one function, then that means we can't have an inverse. Well, why is that? Well, this is not going to have an inverse because recall, if we have an inverse, what are we doing with our x and y values. We're going to switch them, right? So that means if we switch the order here, your domain becomes your range becomes the domain. So we, instead of 0, 3, we would now have 3, 0, 4, 1, and 4, 2. So notice, if we were to switch the order of our x and y values, now we have 3, 0, 4, 1, 4, 2. Does this represent a function? Well, the answer is no, because we now have repeated x values. And that is why our function must be one-to-one, because if we want to have an inverse function, we cannot have repeated y values, because these repeated y values, once we switch the x and y for the inverse function, the repeated y values become repeated x values, therefore making it no longer a function. So that is why a function must be one-to-one in order to have an inverse. So let's go back and look at the function here, f of x equals x squared. Now I want to find, if possible, the inverse of this function. Well, I know you're thinking, well, we just looked at the graph of x squared, we know that's a parabola, and it's not going to be one-to-one. Well, let's look at this closely here. If f of x equals x squared, you probably would guess that maybe the inverse function might be what? The inverse function might be the square root of x. Now, let's look at the graph of this x squared first. Clearly, if we look at the graph of x squared, we know that we're going to end up with this parabola here that's opening up. Now, we know this is a function, but it's not a one-to-one function because it does not pass this horizontal line test. Now, is there anything we can do so that this would pass the horizontal line test? Could we restrict the domain? In other words, if I limit the values that x could take on, would our function then be one-to-one? Well, what's causing this to cross the graph twice? Well, we have this kind of left side of the graph and the right side. So if I was to eliminate this part of the graph over here on the left, if we get rid of that, now would this pass the horizontal line test? And the answer is yes, it would only cross the graph once. So what we're doing is we're restricting the domain so that we only have x values from 0 all the way to infinity. So if we restrict our domain so that we're only looking at 0 to infinity, or values of x that are greater than or equal to 0, we now have a one-to-one function. And if we look closely, then the inverse function here is going to be the square root of x. Now, do we remember the graph of this square root function? Remember, it looks like half of a parabola on its side, something like this. Now, what did we just say earlier about the graph of a function? So if this is our function f, and if this is our inverse function of f, then what about this line here? Remember, there's going to be a reflection of the function and its inverse about the line y equals x. So maybe at first you're not able to have an inverse function, but there's some cases here where you want to make note that if you restrict the domain, you can force the function then to have an inverse function. And later on, if you go on to take pre-calculus 2, this is going to really be very important with some of your trig functions. So keep in mind that we can restrict the domain and force the function to have an inverse, but again, it's only going to be true on this particular domain. So for our example here, this function only has an inverse as long as the domain is 0 to infinity. Now, there's other ways we could restrict the domain. We could have done just the opposite of this. For example, What was the other problem with the graph of x squared? Well, we eliminated this left side of the graph. So what if we did the opposite? What if I eliminate this right side? It's still now a one-to-one function. So here, if we restrict the domain to simply negative infinity to 0, if we do that, we still have a one-to-one function. So the question now becomes, what is going to be the inverse function? Well, we know that if I draw this line through here, y equals x, it has to be a reflection about the line y equals x. And if we think about x squared, we probably think it's going to still have something to do with the square root of x. But now, instead of our graph going this way to the top, we want to put a negative in front of this. Remember, this negative causes a reflection, and this would give us this graph here, and this would be the inverse function. So here we have function f, and the inverse function, again, if we were to fold on the line, the negative square root of x would be the inverse function. Okay, so I want you to realize if we can restrict the domain so that it is a one-to-one function, we then can identify the inverse function. Now, at this point, we were just kind of guessing and going out knowing what we know about x squared and the square root of x to find the inverse function. Let's now look at some techniques for algebraically finding the inverse. And to find the inverse is going to be relatively straightforward as far as the steps. Sometimes it's a little complicated algebraically, but if we want to find the inverse of a function, if we look at the example here, let's say that we have the function f of x equals the cube root of x minus 5. Okay. Step number 1, I'm going to replace f of x with y. Now, really, I'm just putting that in so it looks a little bit nicer because we know f of x is really representing our y. So that just means we're going to write this as y equals the cube root of x minus 5. Okay, that's all that means. Step number 2, we want to basically interchange x and y. And what I mean by that, instead of getting so wordy, is everywhere there's an x, we're going to change it to a y. Everywhere there's a y, we're going to change it to an x. And why do we do this? Well, remember we said the function and its inverse switch domain and range. So it's going to make sense now that our y values become x and our x values become y. And then step number 3, we simply solve the equation for y. So over here, to solve this equation for y, we need to get rid of the cube. So that means the cube root, rather. We need to cube both sides of the equation. So we would end up with x cubed equals y minus 5. And then from here, we would end up with y equals x cubed plus 5. We would simply add 5 to both sides. And I want to switch the sides of the equation so that we have y equals x cubed plus 5. And all I did there was move the y to the left-hand side. And basically then this final step here, step 4, is your y that we just solved for is now the inverse function of f. So that means the inverse function here of f is x cubed plus 5. So we have found the inverse function of the original function, the cube root of x minus 5. And once again, we could verify this. If you wanted to verify this is true, remember we could simply do what? We could find f of f inverse of x, that has to be equal to x, and also f inverse of f of x, would also have to be equal to x. And if you go through these steps here, you're going to find that these are going to be inverses of each other. All right, let's try one more example, and you may want to pause the video and see if you can find the inverse here. If I have g of x equals x minus 4 over x plus 2, we want to find the inverse function of g. So again, maybe you want to attempt this on your own. So if we look at this, if we go through the same steps we did before, g of x, well, we know that's really y equals x minus 4 over x plus 2. And then our step number 2 says that we're going to replace your x with y and your y with x. So therefore, we would end up with x equals y minus 4 over y plus 2. And now we simply solve for y. Now this may be where you got stuck if you tried to do this on your own. There's a couple of techniques you have to remember here, and one in particular. If we want to solve this for y, your first step is going to be, we want to get rid of the y plus 2. So I'm going to multiply both sides of the equation by y plus 2. And by doing so, we're left with, let's see, x times y would be xy, and then plus 2x. So all I did here was distribute the x. So we get xy plus 2x equals y minus 4, because the x plus 2's are going to cancel out. Now this is where you may have had a little bit of trouble. So we have an xy on the left, and over on the right we have a y. The problem is, how do we get y by itself? Well, anytime that you have your variable that we're solving for tied up in two positions like this, and they're not like terms that we can combine, you want to get those on the same side of the equation. So I'm going to subtract y so that we move it over here to the left. So subtracting y, and then we're left with 2x equals a negative 4. And then I want to get the xy minus y completely by itself, so I'm going to subtract 2x. So we get a negative 2x minus 4. Now, once you get the xy and the y by itself, so the only terms now we have on the left contain the variable y. Well, now we can factor that y out. They both contain a y, so if we take the y out, you're left with x minus 1. And now the advantage is, to solve for y, we can divide by x minus 1. So therefore, we have y equals a negative 2x minus 4 over x minus 1. And this here is our inverse function. So we could write this as the inverse function here as negative 2x minus 4 over x minus 1. And there's your answer. Now, pay close attention. The next step I'm going to show you here with this problem is, hopefully I'm not going to make it too confusing, but I want you to realize that we can rewrite this several different ways. For example, if we look at the numerator, we could factor this negative out. So I'm going to just copy this over. We have a negative 2x minus 4 over x minus 1. Now, for example, we could factor the negative out of the top. If I do that, we're left with 2x plus 4 over x minus 1. Okay, so all I did was factor a negative out. Now, that would be an answer. And you could also see this as an answer, 2x plus 4 over x minus 1. This negative could simply be out front in the middle of the fraction. And recall, that's because if we have fractions such as 1/2, we could put a negative at the top. We could put the negative out in the middle, or we could put the negative at the bottom of the fraction. And keep in mind, all three of these fractions represent the same negative 1/2. So we're doing the same thing down here. I took a negative out of the numerator, so the negative could be out front with parentheses where we factored it, or the negative could be out in front of the entire fraction, or we could take that negative to the denominator, and we could actually distribute the negative through the denominator, and we get a negative x plus 1. And then we could rearrange the denominator, and we would have 2x plus 4 over 1 minus x. So notice the x is still negative, the 1 is still positive, so we could write that as 1 minus x. Now, you may have to go back through this again a few times. Now, I didn't come up with or want to show you all of these different ways of writing this to hopefully really confuse you, but I want you to be aware of there's different ways that we could write this answer based on how we handle the negative here. And with your assignments typically being multiple choice, any one of these answers could be there and they would be correct. So just be very careful. If you ever solve and you come up with an answer that's very close, but the signs are not quite the same, see if there's a way that you can rewrite it with factoring out a negative or distributing that negative differently to match up with one of your answers.